Okay, so let's start off with some announcements. First announcement is we'll have quiz 1 Wednesday, and it is over section 2.2 homework. Not had it in my head. Everything was going to be off one section today. So I'm glad you got me clarified early, Magnus. So, all right, no office hours today. I normally have office hours on Tuesday, but today I have to take my mother-in-law's dog to the beauty salon because she can't hear. I'm the interpreter, so she's deaf. So she refused to get hearing aids when she could have still heard. So, all right, and then let's see here. Reminder, no class on Friday, and also no class on Monday, because Monday is Labor Day. So, all right, and our class doesn't mean Friday. That doesn't mean your other classes aren't meeting Friday. So, all right, so let's start off with some 2.2 homework questions then. Any of those, Magnus? Did you have one on 2.2? None on 2.2? All right, Marissa.
So I just got a question on 5.
Okay.
How does that have a limit if the cosine one?
Okay. So on 5 here. All right, so this is 2.2 number 5 where we're given the graph.
Yeah.
Okay, let me get the graph up here. And then let me hear your question again.
I was just saying, you know how we did that cosine graph?
Okay.
When we found out that one didn't have a limit.
Okay, well that was because as we were going into that 1 over x, that 1 over x as it runs around, bounces around that circle faster and faster. So that you're asking, how come our cosine 1 over x, f of x equals this, how come its limit as x approaches 0 of that function does not exist? Okay, that was your question. Versus this one did exist. And so let me flip this back over so I can have something to point to here. So if we were to look at this graph again, what happens is as x gets big, we think about 1 over x, as x is getting closer to 0 here, what's happening to these y values? They're going off to what? Infinity. So 1 over x, get my stick out here, 1 over x, that's going to infinity. Well, that means I'm running around the unit circle faster and faster and faster. The closer I'm getting into 0, the bigger these y coordinates are. So I'm going around that unit circle faster and faster. So I'm bouncing back and forth between -1 and 1. So whatever you say your limit is, let's say I say the limit is 0. Then give me a target, and I'm going to take a target of 1/2. So a target of 1/2 there. Marissa and everybody else, 1/2. 1/2. I should be able to find some interval on our domain here where we stay in between. But as we get there, we keep going back and forth between -1 and 1. It's that bouncing back and forth again, that 1 over x. As we go, we're running around that unit circle faster and faster, so we're just going back and forth. So it's really an oscillating function. So no matter what limit you say, because we go from -1 to 1, if you say I got to stay within 1/2, well, you're going to fall outside that. So now if that was just cosine of x, that's an easy limit. It's that division by 0 as we're going into 0 is the big issue. So, all right. So, but now on this one, let's go back to this one here. Let's just warm up here. So you said number 5? Right. What I should point out, and I think somebody said that, I'm just going to get a chance. Last time I taught Calc 1, the publisher sent me the wrong version of the textbook. And so the first few sections, I have the page numbers wrong. The problems are right. The page numbers are wrong because I ordered, we have the early transcendental functions, and they sent me the one without early transcendentals. And so everybody else had a different book. It took me like 2 sections to get that figured out. So I don't remember who sent me that email saying the page number's wrong. Was that you, Alex? So, is that you, Magnus? Somebody. I didn't even get to it on Friday because I was swamped on Friday. All right, so let's look at this. So what is this again? We got to use this graph here. It says, hey, f of 1. That's saying, hey, x is 1. What's the y coordinate? So we go to 1. What's the y coordinate? The y coordinate is what? -1. This one here, the limit is we go into 1. So it doesn't matter what's happening at 1. It only happens where it happens when we're going into 1. As I go into 1 from the left-hand side, from the negative side, where are these values going to? It looks like they're going to the value of what? 1. And from the right-hand side, from the positive side, they're also going to what? 1. So what is this limit? This limit is what? 1. What is f of 0? F of 0 would be the y coordinate. When x is 0, that would be what? 2. And then how about the limit as we go into that there, as x goes into 0? That would also be what? 2. Notice these match up. These what? Don't match up. They don't have to match up. So, all right. Any other ones out of 2.2? Out of 2.2. All right, let's move on to the 2.3 homework. Let me get my book open to that section, and I'll take those questions. Oh, 2.2 homework. I'll collect it. So those that are turning it in on paper, I'll collect the 2.2 homework. If you turn it in electronically, that's great as well. Oh, I haven't even told you guys how to turn it in yet. Excuse me. I forget. I missed this week. So how did you know that, Leah? You told us last night. Oh, I did tell you. I have collected one of your assignments. Okay. So yeah, fold them on. Anybody else turning it in on pencil and paper? Okay, look. Is that a fancy block you have to pick? Okay. That was one of those fancy things. That'd be cool. That would be cool. Thank you. Everybody else turn it in online? Awesome. I get caught up on my homework. I did not anticipate food poisoning on Sunday in my work schedule. Okay. All right, so now let's go on to section 2.3 homework questions. 49. Let's start. You'll have to ask the second one second, because I only remember one at a time. So, all right, so you said 49 to begin with. So let me get to that section in the book. 7 squared. By the way, if you ever go skiing with me, you'll discover you don't like riding on the ski lift with me because I make you do the prime factorization of the chair numbers as they come down. So 49. All right. The limit as x goes to 4. 1 over x minus 1/4 over x minus 4. Basically, oops, sorry, let me get it on both sides. Basically, we have a rational function here. It's not quite in that form, but we could clean this up and make it in that form. So I have a rational function, kind of a polynomial, although it's kind of a composition of them. Let's put in 4 to begin with, just a little direct substitution. If I put in 4 in the numerator there, Magnus, what do we come up with? If I put in 1/4 all the way, finish it up for me. I get 1/4 minus 1/4, which is? 0. And if I put in 4 here? 0. So I get 0 over 0, which says, hey, does not exist. It says, hey, got to do some algebra. All right. What do we have there? We have the dreaded compound fraction, right? So let's clear some compound fractions. A couple ways of going about this problem. I'll show you the quickest way usually. I like to get rid of these compound denominators. Well, the common denominator is what? 4x. I'm going to multiply numerator denominator by 4x. Multiplying by what? A form of 1. So in the numerator, what happens? Well, as we distribute, we'd have 1 over x times 4x. What would happen there? The x's would cancel. We would just get what? A 4. As we distribute under the second term, we get 1/4 times 4x. What would cancel there? What? The 4's. So we get what? A minus x. So I distributed that through there and cleaned that up. Now in the denominator, I'm not going to distribute. I'm just going to leave that as 4x, x minus 4. Oh, I'm so glad you asked this one today. And this is probably why I have to sign this one. Okay. Anything cancel? Anything? Anybody see anything? I want you to look at this and this. What do you notice about those, class? Caleb? Opposite signs. All right, so they're opposite signs. Excellent, Caleb. Give your former high school math teacher a little kudos later. They're opposite signs. So one thing we could do is we could factor out a negative. And it doesn't matter which one. I'll factor out the numerator, x minus 4, 4x. I could factor out that negative. You notice they're opposite signs. Now, does anything cancel, Magnus? X minus 4's cancel. And notice what happens is you can kind of think about, if you cancel opposite signs, what do you get left with? A -1. So that was an algebra trick that sometimes is nice to know. Occasionally opposite signs pop up, and you got to remember they'll cancel. If you want to factor it out and then cancel, fine. If you want to remember opposite signs, cancel. So now we get the limit as x goes to 4 of -1 over 4x. What is this, class? What type of function is this? A rational function, right? Polynomial over polynomial. We're allowed direct substitution as long as we don't get what? Division by 0. If I put in 4, I clearly don't get division by 0. I get -1 over what? 4 times 4. That's our direct substitution, which is what? -1/16. Thanks for asking that. The only thing better about that is I could have been doing that one yesterday. It would have been better, but can't go back. So, all right. 53? 53 prime or composite? Prime, very good. We got the limit as h goes to 0 of 5 plus h squared minus 25 over h. So we look inside there, and we basically should recognize this as a rational function. It's just not in its regular form. I'll expand it out. So we see a rational function. First thing we always think about, direct substitution. Do we get lucky enough when we put in 0, we get out a number? When we put in 0, well, in the numerator we get 5 squared, which is 25. What's 25 minus 25, class? 0. And I put it in there, I get 0. What form do we have? 0 over 0, which says, hey, do some algebra. Well, there's not a lot of algebra to do, but we could what? Square this out. And when we square this out, you're going to get 25 plus 10h plus h squared. And I like to use the quick formula. A plus b squared is a squared plus 2ab plus b squared. Or you could FOIL it on the side there, Magnus. I won't take my time to FOIL in this class. So we square out that 5 plus h. We get 25 plus 10h plus h squared minus 25 over h. All right. What do we see in the numerator we can deal with? 25's cancel. And then stare at the rest of that for a second. Do you see anything that will factor out in here? Oh, an h. So we'll factor out that h. Factor out that h, we get what? 10 plus h over h. I factored out the h from 10h. Leaves behind a 10. H squared leaves behind an h. Now, you see that'll cancel now? These h's will cancel. And those that took college algebra from me, you know, this is when we do our little happy dance in our head because that's the step we were working towards. And then now what do we have inside that limit, class? A good old polynomial. And we love polynomials because we can plug in 0. All right, Magnus? What is 10 plus 0, Magnus? 10. So our limit is 10. And so those that took college algebra and your teacher was showing you the difference quotient and said only those select few will get to ever see why we do it. Now you can come on in. I was wondering who we were missing. Durston. No. You said, you ever sit here? Oh, come and get your spot. It doesn't bother me. All right, Marissa. 47. Take your spot. Because I'll start calling you that person's name. All right. It is Durston, right? Dustin. Oh, man, why did I put an R in there? All right, 47 you said, Marissa?
Yeah.
The limit as h goes to 0, 16 plus h minus 4 over h. Okay, so let's just mentally plug in 0 right now. If I plug in 0, this little mental step, 16 plus 0 is what? 16. What's the square root of 16, Marissa?
4.
And then 4 minus 4?
0.
Then I put 0 down there? 0. So what do I have here? I got 0 over 0, which says what in limits? Do some algebra. All right. So those of you that told your high school math teacher you're never going to rationalize a numerator ever again in your life, you were wrong. Because you joined the select few that actually went on to take calculus. So a lot of the algebra you learned was only for calculus. So but lucky you made it. So we want to get rid of, there's not a lot to do down here, but we have a numerator here. And what are we going to do? We're going to rationalize the numerator. All right. And this hinges off of the fact, rationalize means get rid of the radical, by the way. A squared minus b squared. Squares get rid of square roots is of the form a minus b, a plus b. So we're going to try to build an a squared minus b squared because square and square roots, what, cancel each other out. So what do I have here? I have an a minus b up in the numerator. What am I missing? An a plus a b. So if I do it to the denominator, or numerator, I must also do it to the denominator. I'll multiply by a form of 1. Okay, so what am I multiplying? Form of 1. So it functions equivalent, it's just in a different form. All right, now in the numerator, what do we have? We have the form a minus b, a plus b, so what are we going to end up with? A squared minus b squared. So I'm not going to FOIL it out in calculus 1. I'm going to say this becomes the square root of 16 plus h squared minus 4 squared. A squared minus b squared. In the denominator, you'll discover you usually don't like to multiply out because you're hoping something's going to cancel. You're hoping to cancel out the 0 and the 0. All right, so what happens here, Marissa? Square and square root cancel, right? So they cancel. So then what do I really have here? I have 16 plus h minus 16. What's going to happen on the 16s? They're going to what? Cancel as well. So that will cancel that. So in the numerator, what do I have left? I have simply an h. Everybody see what happened in that numerator? And notice I will do some of the algebra steps in a calculus 1 class in my head because you're going to be doing in your head as well. So if you have questions, always ask. Now, Marissa, do you see anything that'll cancel? The h's. And that what that really just canceled was the 0 over 0. So now we're going to get a number. So we cancel the h's in the numerator. What do we have left? Well, if everything's gone, we don't have a 0 left. We have what? A 1 left from factoring. And down here we have 16 plus h plus 4. Now, technically, we could do all those things. We need to make sure this is a square root's not going to a negative number underneath. When I put in 0, where's that headed to? 16, which is definitely positive. So let's put in 0. So this will become 1 over square root of 16 plus 4, plugging in 0. Square root of 16 is 4, and 4 and 4 is what? 8, so that reduces down to 1/8. So you got to rationalize a numerator, which how many probably have not done in a while? Probably most of you haven't done it in a couple of years. I don't even think, I usually don't assign the rationalizing the numerators in the algebra class either. All right, any other ones out of that section? We definitely hit the good ones. Any other ones? You have one?
Just that one.
Just that one? All right. So, okay. So now we have our, whatever section that was, 2-3 homework, right? That was 2-3?
Yeah.
All right, so those that are turning it on paper, I'll collect that one now. And those that turn it online, that is fine as well. It did get a lot less stressful questions on how to post homework assignments, so that was... Oh, try to do them separately from here on out.
Yeah, I did teach you online.
Oh, it's online?
Yeah, so.
All right, I'll grade that one first, so I won't count the L.
Okay. Yeah, sorry.
That's all right. Have all the home? You turned yours online, Marissa? Yep. Have all the homework? So now you should be getting a sense that I'm not as interested in you got every answer right or wrong. What am I interested in? You coming in and what? Asking questions and interacting with me. Because we get to talk about things. If you, first off, we got to talk about what? Opposites cancel, leave behind what? A negative 1 and things like that. So it's very important in my system you come in and ask questions. All right. So now let's start on the next section. And this is section 2.5. Let me go ahead and type that in there. All right. And I don't think we'll finish this section today. It'll be close. What's that? I thought we did 2. Oh, excuse me. We're in 2.4. I am off on my section all day. I swear they added another section in that didn't used to be there. Thank you, Marissa. They both involve infinities, so that was partly my mistake. So, oops. I'll fix that later. Okay. And my notes are out of order. Let me get to page 1 here. All right, so let's go back. We kind of have an intuitive definition of limits already. And let's go back and talk about the limit as x goes to a of f of x. And let me draw some pictures in here. So let's say we have this here. Here's the point A. This is the graph of y equals f of x. And there is L. Would we say, if this was the graph of f of x, would we say the limit equals L on this picture? We would, right? So that's one thing. As we go into A, what's happening to these function values? They're approaching what? The same value from either the left side or what? The right side. Our second picture. We could have this here. We could have our graph of f of x. We could actually have a hole at it. Here's L. And our f of a could be what? Some different thing. Would we say that limit is still L? We would, right? We don't care what happens right at the point, only what happens as we're what? going into that point. And then what's our third possibility? We have a hole at A, but we'd still say what? The limit equals what? A, or L, excuse me. All right, so notice on this one, f of A actually equaled our limit. That can happen. Notice this one, f of A did not equal our limit. That can happen. And notice on this one, f of A is what? Undefined. So those were our three possible limits going in, existing going into A. We could have three possibilities. It could be L and have the match up. It could be L and they don't match up, or it could be L and f of A is what? Undefined. So now we have two new scenarios we want to look at. Let's take a look at the function f of x equals 1 over x squared, which we also could think of as what? X to the negative 2. So reminder, negative exponents hide fractions. All right, so what happens as x approaches 0? All right, so let's get a couple of values in here and then find their corresponding value, 1 over x squared. So let's pick out the value plus or minus 1/10. When I square 1/10, I get what? 100th, right? And when I do the reciprocal of 100th, I come up with 100. Let's get a little closer to 0. Plus or minus 1 over 100. All right, well, when I square 100, I get what? 10,000. And the reciprocal of 10,000, 1 over 10,000 is 10,000. All right, so what's happening here? As we're going into 0, here's 1/10. It's already up at 100. Here's 1/100th. It's already up there at 10,000. What's happening here? As we go into that side, it's looking like this. And as we go into this side, it's what? Looking like this there. The closer we get to 0, what's going to happen? Those values are going to what? Get bigger and bigger. Why are they going to get bigger and bigger? Because of what? The reciprocal squared function. Okay. So what would we say then? The limit as x approaches 0 of this function, f of x, the limit as x approaches 0, 1 over x squared. Well, it's not a finite value. We could say does not exist, but we could even be a little bit more specific, and we could really say what's happening to those function values. We could say they're really headed to what? Positive infinity. They're getting bigger and what? Bigger. All right. Love it when you see a typo in your notes. All right, so luckily I didn't teach the typo. All right. So now let's look at the same graph again, but now let's look at what happens when x goes to positive infinity or when x goes to minus infinity. So now we're not going into a specific value, but we're going out to the far left or out to what? The far right. Well, as these x's get bigger and bigger, well, first off, 1 over x is never going to be 0 because the only way a fraction can be 0 is what? The numerator has to be 0, and 1 is never 0. So they're going to get closer and closer to 0. So it looks like those function values are leveling off to what? 0. So we'd say the limit as x goes to positive infinity of f of x equals 0. They're getting really close to 0. And we could also say the limit as x goes to negative infinity of f of x also what? Equals 0. So now we're allowed to, as x goes off to negative infinity, what is that? That's off to what? The left, my right. And as x goes off to positive infinity, we're looking at what? The right. So now we're looking at far left and far right. Magnus.
Why wouldn't the one be 1 divided by 1 over? That's continuous.
Well, first off, we should point out there, infinity is actually not a number. It's a direction. There is no actual number infinity. It just says, hey, when you're going off to infinity, it just means you're going way out there. But it's not an actual number. So what we really want to learn is 1 divided by a number is getting bigger and bigger, going to infinity. That limit is 0. And 0 is a number. All right? So think of it this way. If you have $1 and you get infinitely many kids, how much is each kid getting? Nothing. So, but infinity is technically not a number. But you're on the right track. So, all right. So let me draw a perfectly drawn graph here. You're going to have to bear with me a second. Matter of fact, hang on a second. Intermission time. Stand up and talk to each other. I will draw this perfectly drawn graph so you won't have an idea what it looks like. Find out what people are doing. If you need to study together for the quiz tomorrow, I'll let you do all of that stuff. All right, give you a chance to copy this graph down, then we have some questions to ask about this graph. Yeah, that's what I thought too. So this is the graph of y equals f of x. Got a couple of dotted horizontal lines, you got a dotted vertical line, and go ahead and give you a second to copy that down. And while you're doing that, I'm going to reorganize my notes. Okay, and I'm going to let you try these problems first because we don't get a lot to try on these problems. So let me give you the problems I want you, the limits I want you to try to read off this graph. I want you to find me the limit as x approaches a of g of x. I want you to read me the limit as x approaches negative infinity of g of x. And I want you to find me, oops, sorry there. the limit as x approaches infinity of g of x. So see if you can read me off those limits just using your intuition. Well, let everybody read them. But since you're so eager, I'm calling on you first, Tristan, too.
So you called the graph f of x, and that's
Oh, and I wrote g of x. Oh, man. There we go. I'll fix that. We're back in action now. Tristan, what's the limit as x goes to a? Infinity. And we know that because as we're going into a from the left side, from the negative side, those are getting bigger and bigger, right? As large as they want to be, likewise from that side. So that is infinity. All right, Brian, as we go to negative infinity, where are those function values headed to? M, right? As we're going to negative infinity, we got to go, and it looks like they're what? Approaching, and this is our notation here to say, hey, if this crossed M, I'd have to show it to you. Since I don't show it crossing, it doesn't cross. It's what? Approaching it. So that is correct there, Brian. Very good. And Miguel, how about positive infinity? How about not A, but how about L? You might have thought that was an A over there.
Would you not put x approaching positive infinity or for the limit? Because otherwise.
On this one?
No, for the last one.
I just have infinity. So if I have infinity, that really means positive infinity.
Okay.
Yes, so if I don't write plus infinity, that means infinity. And as we're going bigger, this is what it should look like. It's what? Leveling off. And that is what? In L over there. So it's like that. So, all right, so we don't normally write positive infinity, although sometimes I do in the beginning just to remind us. So, all right. Questions on reading that graph? All right, so let's make some definitions. Make sure this, yeah, it's still recording. All right, so let's make some definitions. And these are really informal definitions. All right. All right. And the first one we're going to define is for when we're coming into A and our function's going to what? Infinity and beyond. For you Buzz Lightyear fans out there. All right? Even that reference is probably still getting too old. Because most of you weren't born when Buzz Lightyear came out, so. All right. Suppose. How many saw Buzz, what was it? Toy Story, that's the name of it. In the movie theater. Oh, in the movie theater, yes. It's different when you see it in the movie theater. All right. Suppose F is defined for all x near A. So we got a function and it's defined near A. Now near is not a definite term. Mark's who we're missing. Because Mark's still close enough to get, he may feel he's not near to me, but I can get him with a spitball when I need to. So near is an arbitrary definition. That's why these are called informal definitions. So near A. If F grows arbitrarily large. If f grows arbitrarily large, arbitrary is kind of an ambiguous term too. So if f gets big, for all x close to a, closer we get to a, f's getting bigger and bigger. Then, close to a but not equal to a, then we write the limit as x goes to infinity of f of x, not as x goes to a, excuse me, as x goes to a of f of x equals infinity. Started jumping in the next section. All right. So this says, hey, closer you get to a, the bigger those function values get. And if that happens, what do we say? We say that limit is what? Infinity. And then we could write an equivalent definition for what? Something like this here. Here is a. And what would happen here? What would we say this limit would be? We'd say this limit is x approaches a of f of x. What do you suppose this one is equal to? Negative infinity. And it would be a very comparable definition, but except they'd be what? Arbitrarily small. Okay. So this means we can now write what? Plus infinity or what? Minus infinity? When what? Both sides are either going to what? Minus infinity, or what? Both sides are what? Going to plus infinity. Okay, so let's look at a graph now. Let's take this function here. F of x equals x squared minus 1 squared. Copy that down. What two values do you think would be interesting in looking at for limits? What ones would be interesting to look at? What causes division by 0, class? Oh, no, wait. I saw a hand up. Is Alicia? What two values would we be interested in? 1 and negative 1, because those are what? Division by 0. So the two interesting ones we'd be interested in is looking at the limit as x goes to 1 of f of x, and the limit as x goes to negative 1 of f of x. And we're going to do this via a graph. All right, so let me get a graph out here. And this is the time where, okay, if you really wanted to buy a TI-84, this would be the good time. But for us, what are we going to do? We're going to use GeoGebra. I'm just going to open up a calculator here. Have we used GeoGebra yet in this class? I've showed a few things in GeoGebra. All right, so if you haven't started playing with it, I kind of recommend it. It's cheaper than a graphing calculator. And so let's see here. I'm going to type in f of x equals, and that's a fraction, right? So I like to start by hitting my fraction. You can kind of see my fraction bar up there. And the numerator is x. And then the denominator, I'm going to start off with a left parenthesis, x. And then to get to the power, I use the caret key, which is shift. What is that? Shift 6. And so now I'm up there. I'm still up in exponent land. I arrow down, -1, and then what? To the x squared power. And there we go. And now sometimes it's even nice to have a couple of lines in there. And the two lines we might be interested in are what? X equals 1 and x equals -1. And let me make those dotted real quick. Make that one dotted as well. Okay. And we'll zoom in there. And how's that read there? Is that, let me put it on both sides now. Oops. These should be ones. So I want you to read me off those two limits. The limit as x goes to 1, and the limit as x goes to -1. Give me a minute to read off those two limits. By the way, on an exam or a quiz, if we needed to do a graphical approach, what am I going to do? I'm going to provide you the graph. Homework, use your TI-84 or GeoGebra or Desmos. Yeah, we don't use graphic calculators at all. They're banned. Okay. You can pull it back out in Calc 2, but not in Calc 1. Okay.
Do we need it?
No. No. You don't need a graphic calculator at all. Matter of fact, for the most, I actually own a couple of graphic calculators, but I just got them back because I sent my graphic calculators with my kid to college because I never use them. So I don't think he used it much either at UW. So, all right. So let's see here. What were our two limits again? Oops. I want to stay on this one. Change the wrong one. I wanted to limit as x approaches. Let's start off with 1. As x approaches 1, so as I approach 1, approaching 1, what's happening to these y values? Getting off to what? Infinity, right? Likewise on this side, they're also going to what? Infinity. So what would we say on this one? We would say infinity. All right. Then how about -1? As we're going into -1, what's happening to these y values? Looks like they're going through the floor, right? That's what? Negative infinity. Likewise from the other side, what? Negative infinity. So this one would be what? Negative infinity. All right. So we like to have an understanding of what's happening even around function values that are what? Undefined. All right. So now let's look at this one. Let's take the function h of x, which is 1 over x. That's one I recommend you should be able to graph from memory. So I'm going to give you a second, see if you could graph that one from memory from previous. This is one of those graphs it's nice to know. Remember from algebra a couple of semesters ago, Tristan? 1? This is one of our toolbox functions. 1 over x looks like that right there. We call that the reciprocal function. There are some functions we just kind of like to know their graphs of. This is one of them. All right. So find me the limit as x goes to 0 of h of x. How about it, class? Cadence, do you have an intuition on this one? So let's see here. As we're going into 0, so that means what? Two-sided, right? So I'm going into 0 from the left side. What's happening to these y values? Getting smaller, right? Off to what? Negative infinity. Left side, what's happening to those y values? Positive infinity. All right, here's your tough question today. Negative infinity equal positive infinity. Yay or nay? Nay. First off, they're not numbers. But what's this conclusion? Does not exist. Now, if I asked you to find me these, the limit as x approaches 0 from the positive side, and the limit as x approaches 0 from the negative side, go ahead and see if you can find me those two values. We haven't talked about one-sided limits, but it's similar to our two-sided limits. We are going to get this section done today. So as I come into positive, right? So this means I'm coming in from positive infinity, right? The positive side. So where are those y values going now? Those y values are going to what? Infinity. And we don't have to worry about the other side. So this would be what? Infinity. From the negative side, the negative there, we're going to what? Negative infinity. So the one-sided limits exist, but they're not equal. That's why the two-sided limit, what? Does not exist. Okay, so these are very informal definitions. Let's go ahead and put up another definition. This one is not informal. Definition. If the limit as x approaches a of f of x either equals positive infinity or minus infinity, the limit as x approaches a from the negative side of f of x either equals positive infinity or minus infinity, or the limit as x approaches a from the positive side of f of x equals positive or minus infinity. So if any one of these limits happen, and there should be a key word there, key word is or. They may not all happen, but any of these conditions happen. One of them is infinity or minus infinity, or any combination of them. Then the line x equals a is called a vertical asymptote, which we often abbreviate VA. So you've seen vertical asymptotes in your previous days, math days, but here's the actual formal definition of a vertical asymptote. They could not give you that in college or in your high school algebra class, because you didn't know what a limit was. So they just told you to approach it and got really big or something informal like that. So if we went back then to this graph, what would we say x equals 0 is? We'd say x equals 0 is what? A vertical asymptote. And we have x equals 0, vertical asymptote. If we went back up here, x equals a is what? A vertical asymptote. It's basically a vertical line. If we were to zoom in really close, these graphs would look almost like vertical lines. Although they don't ever quite go vertical because they're functions. All right. So let's take an example now. Let's take g of x equals x plus 3, x plus 2 squared, x minus 1. Okay. So, get that copied down. No peeking at it. No peeking at it. So, first thing I want you to say to yourself is, what type of function is this? Rational function, right? Polynomial over polynomial, and no, we're not going to multiply this out. All right. Where are its undefined points? What causes undefined again? Division by 0. So what x values can't we use in this function? -2 and what? 1. So we know x cannot be -2 and x cannot be 1. So what are these possibly going to be then? Spots of what? Where vertical asymptotes pop up. Now, one more thing. I want you to find me, just got to remember which axis. What is its x-intercept? Visual inspection. What would make that function equal to 0? What x value would make that numerator 0? -3, right? G of -3. And the only thing you have to do is make sure it doesn't cause 0 denominator. It doesn't. G of -3 is what? 0. So we already know 1 point, and we know 2 possible vertical asymptotes. All right, so let's get a graph of this now. And now you can graph it there. But I always like to encourage my students to turn on the brain first. All right, so let's get a graph of this. Turn this off, and we'll call this one g of x equals, and what am I graphing here? A rational function, x plus 3 in the numerator, and x plus 2 squared times an x minus 1. Okay. Now let me put in the two interesting vertical lines we thought, two lines we thought would be x equals -2, and we said what? X equals 1, and let me make those dotted just to help see them. Okay. So from the graph, does it look like x equals -2 a vertical asymptote? Yeah, it does, right? Because if we're going this way, they're going to -infinity. If we come in this way, they're also going to what? -infinity. And then how about x equals -1? Is that a vertical asymptote? Excuse me, x equals 1. Is that a vertical asymptote? Yeah, because these are going to what? -infinity. And on this side, it's what? Going to positive infinity. Remember, it can be any combination. Why? What makes these go to the same direction and this one skip? This is going to -infinity. That one's going to positive infinity. Anybody tell me what causes that? It has to do with the square versus the odd power. Let me pull this back over here. Why did at x equals -2 they both go the same direction? It has to do with that square there. If it's a square, they're both going to go the same direction. Why is it the opposite? Because that's only a single power. And that'll be a little bit you'll pick up along the way there. So then if we were asked, let's get that graph over here, just so we can see it there. So then let me ask you, what is the limits? Find me the following limits. The limit as x approaches 1 of g of x. Find me the limit as x approaches -2 of g of x. And find me those two limits. This is our last example, by the way, Marissa, so you're not missing much. So if you're like, oh, I got to go watch the last 15 minutes of the tape, you got to watch like 3 minutes if you want to.
Thank you.
Mm-hmm. Have fun. Good luck on your competition. Your is it a match? Do we call them matches or games? It's a okay. Home game? It's here? No, it's not here.
It's
Okay. Colorado. So I was going to say it's home game. Everybody should go see it today. By the way, I always encourage my students to go to events. You may think they're free. You actually paid for them with your student fees, so you might as well take advantage of them. You only get to go to college once unless you're lucky enough to be a professor, and then you never leave. What's that? Yep. It's a good lifestyle. I can't complain.
They're paying you to say that.
They are not paying me to say that. So as x goes to 1, well, what's happening as x goes to 1? From the left-hand side, from the negative side, as x goes to 1, where are these function values going? -infinity. How about from the positive side? Positive infinity. So what would we write on this one? This one would be what? Does not exist, since the limit as x approaches 1 from the negative side of g of x. What was that again? From the negative side is what? Negative infinity. And the limit as x approaches 1 from the positive side is what? Positive infinity. The one-side limits are what? Not the same. And on a does not exist, you'll have to tell me why. Now, what's the limit as x approaches negative 2? It is what? Negative infinity, right? Now, what do we know? Well, we know x equals 1 and x equals negative 2 are what? Vertical asymptotes. All right. So that concludes section 2.4. So tomorrow we'll go to 2.5. And in 2.5, we'll be looking at the off to infinity again, plus or minus infinities. And we'll have our quiz at the end of the hour. And I said the quiz was over what? Section 2.2, right? 2.2? All right. Reading graphs and stuff. So question, Magnus? I thought I was going to answer it there. So, all right. Any other questions? All right. Well, have a good day.